Welcome to a lesson with Dr. Powell. Let's take a look at y when we mod out by p to the n and look at the multiplicative group of units that it's cyclic. Why is that cyclic? Let's take a look at the p-adic integers and its multiplicative group of units. Now, when we mod out by p, meaning that we mod out by a normal subgroup, 1 plus PZP. This is a multiplicative subgroup of this, and we mod out by it. It's like we're saying this is behaving like 1, which is like saying PZP is behaving like 0, or P is like 0. So we're really modding out by P when we mod out by this. And we end up getting the multiplicative group of units of ZPZ. Okay, so now in this we have now we have a couple things going on. This sequence right here is an exact sequence because this right here is the kernel of this map by definition. We also have that it splits, so it's a split exact sequence. If we consider the Teichmuller character that goes back this way, namely, if we take some element here, say x or whatnot, we lift it up here to an element of ZP. Let's also label that as x, so a lift up here, so something that that actually maps down here to it. So anything, just take any lift at all, and you take that lift and you raise it to the pth power. Then you raise that to the pth power, then that to the pth power, and so forth. So it looks something like this, and you take a limit. This limit exists in the p-adics, and gives a nice homomorphism that goes back this way, which makes this a split exact sequence. Okay, so let's now use that idea that we have a split exact sequence, and we want to turn this split exact sequence into a split exact sequence for z p to the n z. And we can do that relatively simply using the fact that if we consider a subgroup of this, which is 1 plus p to the n zp, and we have this inclusion, and then naturally this inclusion right here, we can think of that as being a group, as being a map that comes, could think of that as being a map that comes from 1 plus p to the n zp. Okay, like that, where we can even like put an equal sign right here. Well, this is just a nice morphism going that way. And then as we go through here, since this is in the kernel, it's going to factor through 0. So we can do that, 0, and come down. Now, what we've just created, so this 0 map naturally has a nice splitting. We've created a split exact sequence of chain complexes right here. So we have a chain here, a chain here, and a chain here. And if we put in zeros down, up and down below, we have a split exact sequence of chain complexes. And the category of chain complexes in a billion group. This is a nice thing here. And now, in particular, if we take the homology of this, thinking of these arrows as being down, and we take it in this position, so we're taking the kernel of this map over the image of that one, which is just the quotient of this by that, that by that. If we take the homology, which is just the quotients here, we end up getting a split exact sequence out of that. since we're just applying an additive functor to a split exact sequence, and we get a split exact sequence out, which is kind of nice. That's partly because compositions are preserved, and if you have the identity happening here by a composition, that's going to be preserved too by the functor, and we're going to get something we're going to get the right surjection or apomorphisms and monomorphisms, so that we actually get a split exact sequence here. So that split exact sequence ends up being, in this case, so this modded out by that, let's just call that U. And then over here, when we mod out that, that's simply going to be like modding out by p to the n. So it's simply going to be z mod p to the n z in the group of units. And then over here, it's just going to be z p z cross. So we do get a nice split exact sequence where this is just the image of omega in the, or the Taekwondo character here in that homology functor, or just the modding out, really. I mean, that's kind of highfalutin language for that. So which was completely unnecessary, yet it provided a really simple, quick explanation why we have this nice split exact sequence. So then in having this split exact sequence, this can be thought of as the direct product or the direct sum of these two guys right here. The size of this is p minus 1. Now the size of this in here is actually p to the n minus 1. Notice how these are co-primed to each other, which means that if both of these happen to be cyclic, that would force this guy to be cyclic. And a generator for this would be a generator for this guy, put over here by the splitting, and then take a generator for this guy, put over here by this arrow, and then multiply them together here. And that would be the generator right in here. And we would be done. So really all we have left to do to consider is why is U cyclic? So let's take a look at that idea now. Okay, so first of all, we are going to talk about why, let's see, if we have 1 plus PZP, we actually have a continuous homomorphism that's also an isomorphism. So a continuous isomorphism here between PZP and 1 plus PZP. And here, this group right here is, at least it's generated topologically by 1, or 1 times, or p times 1. ZP is generated by 1 cyclically, at least topologically, meaning that that if you take 1 and 1 plus 1 and 1 plus 1 plus 1 and so forth, so you get all the integers are a dense subset in the p-adic topology of ZP. So you get, there's a generator of PZP, which is P itself, and that is at least the topological generator of that, and via this isomorphism gives us a topological generator of this guy. So let's talk about what that isomorphism is before we continue. And it's continuous. So what it is it's simply just this, you take the power series for e to the x, 1 plus x squared over 2 and so forth. And we take this, notice we're dividing by some things, but that's okay, as long as we pay attention to what our domain is, and we think about convergence, and if we're staying in staying in the right places to output the right things. So if PZP is our domain, let's think about that. So then the valuation of x everywhere here and x squared and so forth, I mean, of these terms is just going to be going up. We're going to have So the power of p here would be like p squared or more, and then p to the fourth or more, and so forth, and it's going to be going up. And then here we'll be dividing by things, and every now and then we'll be getting maybe some more factors of p popping up every now and then, but not very much. So not enough where we're actually going to be converging and our powers are going to be going way up. So we'll get it. So the sequence of partial sums is a Cauchy sequence. It will converge, and that'll be nice. So we get, so as long as our domain is PZP, we have this function sending x to e to the x. This will be convergent on PZP. So that'll be just fine. It's convergent and it's also continuous, because let's see, if you want, for instance, let's suppose that you have some image, so you have like some e to the a, okay, some image, and you take some open set around it, or some kind of, some neighborhood around that's centered e to the a. So maybe you add like some p to the m zp on, and kind of, and you're looking at this neighborhood. Now it's easy to get a whole neighborhood of x that'll actually fit inside there just using this power series and how it converges. If you think about having even if you just did, let's see, even if you just simply did p to the m or p to the m plus 1, so you take x, even if you add, let's just see what happens when we add p to the m zp, so some so x plus some guy there. So here we have in here, so if we did that, so we're going to have e to the a popping, or in fact a, I guess, sorry, because yeah, a plus, so a goes to e to the a, right? And then we're going to be looking at a neighborhood of a. So we look at that neighborhood of a, and we have, so here, just in the first term, we're offset by p to the m times something. And then in this term, we're going to have, we're going to be looking at an expansion, a binomial expansion. And in that, we're going to have powers of p to the m going on. And also x happens to be in PZP anyway, so we're going to have more power. So we're going to be kind of going up the whole time with that, even when we're at the lowest of powers there. And then we're going to be going up in powers, and that just contributes. So really, as we go along, this whole thing, if we vary a by this neighborhood, we're going to still be sitting in this neighborhood over here, which is just kind of a quick little description of what it really is. This really defines a continuous map. This continuous map is also homomorphism, because we have e to the, well, I mean, just by properties of e to the x, it's multiplicative in nature. But the question might arise, well, yeah, that's true if you're thinking about the topology and convergence and definitions and so forth, like in the real numbers or complex numbers or something. But also here it works just fine too. And mainly that comes from a couple of reasons here. You can think of, well, first of all, let's think about this. So this is an additive group, and you have like x plus a, and you want to say that's like e to the x times e to the a. Well, if you look at these two ideas, you think chain rule for derivatives, you think just constant multiple times derivatives, and then plug in x equals 0. We're going to have equivalence all the way down. Since these derivatives are the same at 0, the power series are going to be the same. So we kind of have an equivalence of power series. So it looks like it works with the convergence here. So this is a homomorphism. That works great. Now is it an isomorphism? Well, let's try to get a map that goes back the other way, that inverts this one. Okay, so well, why don't we try the just the log map, log going from here to there. Now we're inserting 1 plus something, so maybe we can look at 1 plus x, the power series for this, and think of, or let's putting in PZP and for x here. So the power series for this log 1 plus x, and we're going to have x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 and so forth. This alternating pattern. Now, if we were to put, okay, so if we were to put e to the x into log, we can almost think, let's see how we have a 1 plus all this, and this is like a 1 plus all this. So when we plug this in and we get this, we just need this whole part over here to be going into this x here in this series. And notice that this part right here, as we put it in, the minimal power coming out is always like an x squared, x cubed, and x to the 4th, which is kind of nice, which means that our first few terms are eventually not affected by what happens over here as we keep on going, which means that the convergence, so we're not going to be using any convergence from the real numbers necessarily, but just kind of, we can actually just limit ourselves to just formal power series in this composition, meaning just in the realm of formal power series, we actually get that these compose nicely to just give us the identity function x to x. So really, we get that these are inverses of each other. So we have an isomorphism right here. All right. The next thing that we need, though, is how does that relate to u now, right? Okay. So 1 plus p zp, all right, we take a quotient of this to get to u. Now this right here, we have this isomorphism, this continuous isomorphism from PZP. We take the topological generator here, 1, and we put it into here, and then we send it to here. The question is, does that become a cyclic generator right over here? Well, what does it mean to be a topological generator? That means what it generates is dense. So we have a dense subset in here, and we're sending it over here. This map is so we have a dense map here, and is this map continuous? Because a continuous image of a dense subset will be dense in here, and since this is a finite set because it's a subgroup of z mod p to the nz, then a dense subgroup is just the whole thing. Especially if we just use the discrete topology here. Well, since this has the discrete topology, then if we take, and the question is this map continuous? Well, if we take the pre-image of anything over here, if we take the pre-image, think about what this map is. We are modding out by like p to the n. Well, that's perfect because anything in a neighborhood, that's even describing neighborhoods over here, so it makes it continuous. So a pre-image of an open set over here in the discrete topology will be open over here, so it's continuous. So that's all we need. So that means that the topological generator over here, which is just the image of p, PZP coming down the chute here, which is just e to the p. So e to the p is the topological generator of this. So we take this and we send it to u, which is just kind of like taking e to the p in the power series and modding it out by what we need to be inside of u, which is just p to the n. So we just take e to the p mod p to the n, and that's going to be the cyclic generator of u. Now, as we discussed before, we take that cyclic generator of u and we multiply it by the Teichmuller character of, we need a generator for this cyclic group, right here. So I just call it G for generator. Okay, so omega G and times that, multiply those together in z mod p to the n z, and voila, we have our cyclic generator of this group, this multiplicative group. Thanks for watching.